you ever learned a scientific fact and wondered, but how do they know that? This happens a lot in physics, which often deals with things that are either very far away, like stars and black holes, or very small, like atoms, electrons, and even quarks. Objects that are so distant or so tiny that no matter how advanced our technology gets, the very laws of the universe prevent us from observing them directly. In this episode, Dr. Shireen Adenwalla introduces us to the nanoscopic world of condensed matter physics, which explains the behavior of familiar solids and liquids, but also strange and beautiful phenomena like superconductivity, superfluidity, and other super things. Shireen explains how the sense of wonder and creativity fostered by the visual arts can help scientists do better science by finding clever ways to visualize phenomena we can't observe directly, and how scientists in turn use scientific principles to create beautiful art. I'm Jocelyn, and let's get verbing!
Well, of course, here everybody studies magnetism, but magnetism is a beautiful phenomenon.
Yeah, it is.
One of the phenomena I'm excited about in general is superconductivity, because once again, that's a many-body effect. You know, you've got lots of electrons, and yet somehow they manage to make this wave function that is macroscopic, right? Yeah, so I think superconductivity is beautiful and exciting and unintuitive.
Yeah, right?
Non-intuitive. That's the word I'm looking for.
It's quantum mechanics at our scale.
Yeah, at the scale of your thumbnail.
I just did a mind-blowing.
So explain what superconductivity is for those who may not know.
So superconductivity and its cousin superfluidity is basically what happens as things get colder and colder is that they organize themselves differently. And this reorganization of the electrons in one case and of the atoms in another allows them to travel freely through materials. That's why in a superconductor, the resistivity drops to zero. And in a superconductor, for example, and they've done these experiments, and I don't remember how long, in a superconductor, you can send in a current with a source, a battery. Then you can close the superconducting loop, take the battery away, and measure how long the current lives in the superconductor, and it can live forever. Well, I don't know about forever, but it can live a long time.
So it's kind of like a normal material would be like a mosh pit at a heavy metal concert, whereas superconductivity would be like line dancing.
No, it's extremely
formal. They pair up and then they're all on ice.
They're they can move smoothly through things without bumping, yes.
The dancing analogy, we have a Funsize physics
Yes,
post
that's very
about
cool.
That.
We have a Funsize physics post. Go look for it.
We will link to it in the episode description. So for more on superconductivity and superfluidity.
Yes, and we have superfluidity on Funsize physics too.
So here we're like the anti-molasses, right?
Yeah,
that was the phrase used in one of our posts.
Yes,
where
superfluids just flow anywhere.
Oh.
They're very beautiful.
So zero viscosity, that
exactly.
thickness that you think of with honey and other viscous liquids.
Pouring is very easy. In fact, I think there's somewhere, I think we tried to get this. If you have a superfluid container, a container with a superfluid, it'll climb up the sides of the beaker.
Yes, I think we do have a video of that. Yes,
video?
I think we have
That's
that video.
Very cool.
It's very cool.
So I did my undergraduate here. I did it was the experimental class, and me and my lab partner, we finished all of our experiments. So we were done and we still had a couple weeks left in the semester. And Herman Bodelon and us two, we tried to create a superfluid. We didn't get the vacuum good enough, but we tried really hard he even bought helium and everything. So we tried to do one.
It should be pretty easy.
Yeah, we did. I know it should be, right? I mean, you can. If
he bought the helium, I think you should be able to do it. You should be able to pump on it. I think
you got to get it down to about 2.7,
2.17. Yeah,
somewhere around there. Yeah,
2.17. What, Brad?
Kelvin.
Degrees Kelvin. Okay, so we're talking very cold. Yes.
Here.
No. Just making sure. So, Shireen, besides superconductivity and superfluidity, what would you say have been some of the most exciting developments in condensed matter physics?
So going back to superconductivity, they now have magnetic superconductors. They've now discovered superconductors that are also magnetic. And
everything's better when it's magnetic.
No, but this is really exciting because people used to think that magnetism and superconductivity could not coexist.
Ah, yes.
And now you have magnetic ordering with superconductors, and that's really exciting.
Yeah,
And
the trains. Because now they can create.
Yeah,
they're
but
not
it's too
exactly. They use
cold.
more of a diamagnet right now, correct?
Yeah.
For the
So superconductors are
maglev
also
trains is what I'm talking about.
perfect diamagnets. They expel
Yeah.
all field. And there's this experiment that I want them to try in the experimental lab. You can cool one of these high temperature superconductors down to liquid nitrogens, and then you can float a magnet above it.
Yep.
Because it just pushes out all the magnetic field lines.
I think I saw a video of that on
Yeah,
YouTube
there's a
one
video,
time.
but I want them to do it because I think it'll be fun.
That'd be fun. Yeah.
Because they have a chunk of superconductor and they have liquid nitrogen. So
Right.
What else are you going to do? I mean,
if you have those things.
all the ingredients are there.
Mhm.
So this all sounds fantastic and awesome and cool. And that's what appeals to me about condensed matter physics, as you know, is just the wow and the wonder factor. But as we've discussed on this podcast before, condensed matter physics also, and perhaps is better known for a lot of the electronic applications that we get out of it. So in terms of those kinds of things, the interesting new kinds of electronics and ways of storing data, what would you say have been some of the most significant achievements there in the last 10 or 20 years?
Well, the many, many different ways that they store magnetic data now, how they store it, how they read it, how they write it. And there's more techniques coming online all the time. This is one of the big questions of our time. I have a picture somewhere of, I think it was an Apple memory in the early 80s. And you can imagine a cube about 10 centimeters by 10 centimeters by 10 centimeters. And they've got these little ring magnets through which they're passing currents. And, they had all of kilobytes of memory, I think. And so magnets have been a mainstay of memory circuits, right? But of memories. But where we've come now, now we have terabytes of memory. That's huge amounts of memory, right?
And basically you
And
need...
cheap.
Packed
And
into
cheap.
a little chip that
Inch,
can
yeah.
fit in your hand.
Yeah. And
All
cheap.
right? Cheap, yeah. And
Memory
that's the
is
great thing
cheap.
about Moore's Law. It just
Yeah.
keeps getting cheaper.
I knew Moore's Law was going to come
Oh,
up
yeah.
here. Yes,
You
Brad
know
had to go
that,
with
but-
Moore's Law. And looking for ways through condensed matter physics, basically sort of reinventing matter itself to try to overcome this.
That's true. That's true because people now have a toolbox of magic materials in some sense that do things that you wouldn't think they would. They have a toolbox of being able to make things very thin or very small, and their behavior is very different than it would be if you had a chunk of it in your pocket. So yeah, our toolbox has expanded tremendously.